Welcome to Signify, a sentence level translation system for low resource Sinhala sign language. Sign language is a visual language primarily used by deaf and hard hearing community as their primary communication method. Sinhala sign language is the main sign language used by deaf and hard hearing community in Sri Lanka. Sign language translation contains two main parts, recognition and translation. Recognizing individual signs from sign language videos is a computer vision task. Translating them back to a natural language sentence is a natural language processing task. What is our motivation? For Sinhala sign language, there are no existing sentence level translation systems are available. The research work on Sinhala sign language is mainly focused on character level and word level recognition systems. For real world application, a sentence level translation system is desirable. In other hand, compared to other sign languages, Sinhala sign language is an extremely low resource sign language. The severe data scarcity, mainly for sentence level datasets, hinders the Sinhala sign language translation. Our main research objective is to develop a sentence level translation system for low resource Sinhala sign language by generating synthetic sentence level key point sequences from isolated sign dataset and transfer knowledge from Sinhala sign isolated dataset as a classification task. The other research objective is to develop a mobile application. The Sinhala sign dataset we are using include two main parts, isolated gloss dataset, sentence dataset. A gloss is a single sign with a specific meaning. The isolated gloss dataset includes around 912 glosses, with each having 5 or more samples. The sentence dataset includes 100 unique sentences, with each having around 20 samples. Both of these datasets were created using 5 different signers. This figure shows the overview of our system. It contains two main parts, pose estimation and translation. Pose estimation is identifying human poses from sign videos. For that, we use an off-the-shelf model called RTM pose. This model gives 133 key points. To identify the signs, we only required upper body movements of the signers like face and hand movements. So, we dropped irrelevant key points and selected 102 key points to the translation part of our system. For translation, we use a transformer model. To encode the post estimation data, we use a stochastic encoder. The stochastic encoder captures the natural variation in signs by estimating a weight distribution instead of point estimations. Available limited data is not enough to learn complex patterns in Sinhala language. Therefore, to generate Sinhala sentence from encoder output, we use a decoder from Embark, which is an multilingual large language model already trained on a Sinhala data corpora. To train the transformer model, we are using a multi-stage transfer learning strategy. To address the data scarcity, we created synthetic Sinhala sentence key point data using Sinhala isolated dataset. That is, we combine different signs from isolated dataset to form a meaningful sentence. The isolated sign videos have different backgrounds and clothing in signers. To overcome this, we are using key points data to create the synthetic data. To ensure a smooth flow from sign to sign, we include interpolated key point frames between signs. This way, we created 320 synthetic key point sentences with each having three samples. To train the transformer model, we are using three-stage transfer learning approach. In the first stage, we are training a stochastic transformer model with German Sign Language data so that the encoder can learn general sign language patterns. In the second stage, we take the previous encoder and attach a attention-based classification head. We train this model with single isolated sign data so that the encoder can update its knowledge to specific single sign language patterns. In the third stage, we are taking previous encoder and attach the embedded decoder. In between encoder and decoder, we are placing projection layer so that it can map the encoder embedding dimension to the decoder embedding dimension. Projection layer also take the average from stochastic samples we are getting from the stochastic encoder. This table shows the results for Sinhala isolated sign classification in different encoder pre-training setups. We got the Hertz scores, which are 79% accuracy and 77% F1 score when we train the first two layers of the encoder after pre-training it with German inception and keypoint data. This table includes the Sinhala sign language translation results in different pre-training setups with and without generated synthetic data. The validation and test datasets were selected in a manner to maximize the coverage of glosses. As we can see in the table, the use of synthetic data has improved the translation results. Also, in all cases, pre-training the encoder with isolated single sign dataset has higher performance than pre-training the model on just German Sign Language data. Let's see a demo of our application.